Hey y'all, today we are going to talk about the product rule. It's another rule that's going to help us determine derivatives without necessarily going back to the definition of derivative. So far you should already understand the power rule and some of the sum and difference rules, the constant multiple rule, the constant rule. So just a quick recap. Remember, the derivative of any constant is 0. If you have a constant multiple in front of a function, then you just take the derivative of the function and then multiply it by whatever that constant is. So for example, if you had 3x to the 5th, if I want the derivative of that, you would say, okay, let's take the derivative of x to the 5th, right, which is 5x to the 4th using the power rule, and then go back and multiply it by the constant out front. That's the constant multiple rule. And then we have the sum and difference rules, which basically says if I'm taking the derivative of a sum or a difference, that's the same as taking the sum or difference of the derivative. So in other words, if you have f plus g, and I say find the derivative, then you just say, okay, it's f prime plus g prime. Pretty straightforward. Now, today's rule is going to seem like it appears to have the same pattern or the same relationship, and it does not. We do not want to fall into that trap, and you'll see what I mean in just a second here. So with these concepts, if I were to say find the derivative of these expressions or these functions, many people might already have an idea of what they should do. And the guess here, for the first one, for example, you got d dx of 2x cubed plus 7, and then times x to the 4th minus 3x. So the initial thought for most students is, well, it's just like the sum and difference rule. We're multiplying two things, so we'll just take the derivative of each of those and multiply them. So if we take this derivative, remember, multiply the exponent to the coefficient, so you get 6, and then we subtract 1 from the exponent, 6x squared. The derivative of any constant is just 0, so we don't have to write that down. The derivative of x to the 4th is going to be 4x cubed. The derivative of negative 3x is just negative 3. What's the slope of a line? The slope of the line is the derivative of the line, basically. Now from here, we might say, okay, well, we took the derivative, so we'll just simplify this and get 24x to the 5th minus 18x squared. And that's where some students might say the answer is, okay? Now, if you were to use your calculator, like I've told you not to do, to find the derivative function, you would find that it does not match this. This is a big no-no, okay? Same thing with these other guys. The initial thought on some of these, we'll do the next one, for example, based on the ideas that most students have when they go into this lesson, okay? X to the 4th times radical x. Well, okay, well, I'll just take the derivative of the first thing, that's 4x cubed. And then the derivative of the second thing, I got to rewrite that as a fractional exponent. So the derivative of that's going to be 1/2 x to the negative 1/2. And then maybe we simplify it from there. 4 times 1/2 is 2. X to the, that'd be 6 over 2, so 5 over 2. And so you'd call it that, right? That's what you did. The derivative of the first thing times the derivative of the second thing. In fact, that is incorrect as well, okay? So we got to be careful with that. We got to be careful with that, and of course I'm expressing a little different there. And then some of you might say, well, I can do the last one, 5x to the negative 3rd times natural log of x. We've kind of already explored this one. We haven't proven it yet, but we've explored it. The derivative of this guy is going to be negative 15x to the negative 4th, and the derivative of natural log of x is 1 over x. And so you say, okay, well, that's maybe where it's at. So maybe it's negative 15 over x to the 5th, you might say. But again, you would be wrong. Okay, and again, I encourage you to maybe plug it into your TI-89 calculator and see that they don't match, that they're not equivalent to what is implied here. Okay, so we have to use a new rule. This new rule is called the product rule. Now, I'm not going to prove it in this video. You can find the proof in another video in the playlist, but we're going to go ahead and use it. The product rule basically says this, that if I have f of x times g of x, if I have two functions that I'm multiplying together, and I want to find the derivative of that product, the derivative of that product, you go through this routine. It is, the first thing is the derivative you say the derivative of the first thing, so it's the derivative of f. We'd also call that f prime of x, by the way. That's just another way of writing it. So the derivative of the first thing times the second thing. So I should probably put brackets around this. So it's the derivative of the first thing times the second thing. Notice I did not take the derivative of the second thing. I only took the derivative of the first thing. And then we add to it the derivative of the second thing, and then multiply that by the first thing. Okay? So another way to write that would be the derivative of g of x is g prime of x, and then just times f of x. The product rule says if I want the derivative of a product of two separate functions in respect to x, I take the derivative of the first thing and then multiply it by the second thing. Then add the derivative of the second thing and multiply it by the first thing. Okay, that's the product rule. That's the product rule. Now I'm going to, on the little lesson here, you're going to see that I use different representations. If u and v are both differentiable functions, so u and v are like f of x and g of x, then the derivative of u times v, u being function, v being function, is the derivative of u in respect to x. So you can see that here, the derivative of u in respect to x is like f prime, times v, so that's times g, the second thing, plus the derivative of v in respect to x, that's g prime, times u, which is f. Okay, so that's the product rule. Again, in words tend to be a little bit more useful here in terms of remembering, memorizing the product rule. The derivative of a product is equivalent to the derivative of the first times the second plus the derivative of the second times the first. Okay, the derivative of the first times the second plus the derivative of the second times the first. Okay, so let's go ahead and look at an example and let's explore it two different ways. I picked this particular function so that we can verify that our answer using the product rule makes sense. So we have 2x cubed plus 7 and times x to the fourth minus 3x. And we're looking for the derivative of this guy. Now, normally you might try something. We know that just finding the derivative of this and the derivative of that and multiplying doesn't work. So maybe we can rewrite this by simplifying it and putting it in standard form. So multiplying all this out, we get 2x to the 7th minus 6x to the 4th plus 7x to the 4th minus 21x. And then we can simplify that a little bit further by combining like terms. So we end up with actually plus x to the 4th there, and then minus 21x. And then when I go to take the derivative, I get f prime of x equals 14x to the 6th plus 4x to the 3rd minus 21. Now I can be pretty confident that that is correct because this is just algebra skills here, and then the power rule is pretty easy to follow along. So now if I want to verify the product rule, let's go ahead and take the derivative of f using the product rule and see if we end up with the same answer. Well, remember the product rule right up here says we take the derivative of the first thing, so this is my first term, that would be 6x squared, times the second thing, x to the fourth minus 3x, plus the derivative of the second thing, so that would be 4x cubed and minus 3, times, so we want to put parentheses around that whole binomial there, times the first thing, so times 2x cubed plus 7. So there's the derivative. The question is this equivalent to that? And so now it's just a matter of algebra. So we're going to go ahead and distribute. We end up with 6x to the 6th minus 18x cubed. And then here we end up with plus 8x to the 6th plus 28x cubed minus 6x cubed minus 21. And then we'll combine like terms. F prime of x would equal 6x to the 6th and 8x to the 6th is 14x to the 6th let's see, 18x cubed plus 28x cubed is 10x cubed, minus 6x cubed is 4x cubed, okay, and then minus 21 left over. So you can see that they produce the same derivatives, so that kind of verifies, at least for this example, that the product rule does work. Now, some of you might be saying, well, it seems to me like that was more work than this one was, and I agree with you. But if we have some really complex expression, something that's not polynomial, something that maybe mixes trig functions with exponential functions, or even trig functions with polynomial functions, when you have anything more complex, you're going to need the product rule to be able to take those derivatives effectively. The other thing I want to say before we go on, this tends to be a perpetuating problem throughout the entire year. Students always, for whatever reason, have a hard time recognizing that they should use the product rule. The product rule is always used whenever you're multiplying things. Now I'm going to show you a quick example before we go to the next thing, because you might go, well, this might help you see it. If you see these rules in every function, it will help you understand them more. So if I give you something where I want the derivative of, let's say, 10x to the fifth, just something simple like this. Obviously, we can do the power rule. It's just going to be 50x to the fourth. We understand that. But we can actually apply the product rule here. We can recognize that this is a product of two things, where the first thing is 10 and the second thing is x to the fifth. So let's apply the product rule. What's the derivative of the first thing? Well, the derivative of 10 is 0 times the second thing, so times x to the fifth, plus the derivative of the second thing, which is 5x to the fourth, times the first thing, so times 10. Simplifying this, is obviously all 0, and we're left with 50x to the fourth. You can see that the product rule still applies here. My point is, any time you see multiplication, you should be thinking product rule. Now here, yes, we do see multiplication. You don't have to use the product rule here, but it should pop up in your brain, at least for a very long time, that product rule is an option. You never want to forget the product rule or the fact that you can use it, because students just fall into the trap of taking the derivative of the first thing, multiplying it by the derivative of the second thing. No, no, no. Okay? All right, let's go ahead and take a look at some practice problems here that I want you to give a shot. First one, so go ahead and push pause on these, and when you're ready, compare it to my answers to see how you're doing. So for the first one, we're looking for the derivative of this product. So the derivative of x squared is going to be 2x times natural log of x plus the derivative of natural log of x, remember, is 1 over x times x squared. And now this can simplify a little bit here because we got 1 over x and x squared. So this can actually simplify to 2x times natural log of x plus x. And I'm going to put parentheses around that x for natural log, so I know I'm only taking the natural log of that x. All right, so that's the derivative of the first expression or first function there. The second one says let y equal 3 over x to the fourth times sine of x. What is y prime? What is y prime? Now, this one you have to be careful on, right? You got to be careful on. You can't just take the derivative of x to the fourth. Okay? Common mistakes at the beginning are, well, I'll just take the 3 and then do 4x cubed on the bottom. That doesn't work, and you recognize that we have a function that is in the denominator. If that's the case, we've got to either use a rule called the quotient rule, we'll get to in the next lesson, or we have to rewrite this in a way that we can use one of the rules that we know. So what I'm going to do is I'm going to go ahead and rewrite this as a negative exponent. So it's 3x to the negative fourth and then times sine of x. From there we can apply the product rule. So the derivative of the first thing is going to be negative 12 x to the negative fifth, right? We subtract 1, and then times sine of x plus the derivative of the second thing. So we should know from prior units, we did a little discovery on this, the derivative of sine of x is actually cosine of x, and then times 3x to the negative fourth. So that's our derivative. We can simplify that a little bit if we wanted to, move the exponent down. So you get negative 12 times sine of x over x to the fifth. And then here we would end up with plus 3 cosine of x over x to the fourth. Now, do we have to make it look like this? Not necessarily. There's not a need to simplify anything unless the problem has to continue, unless there's multiple parts of this problem and we have to use this, and this might be the more efficient way of using it. But this is a totally valid answer up here as well. Okay? For the third one, let me go ahead and erase these. The third one here says f of x equals x to the fourth times radical x. Now, we are looking for, notice the notation there, we're looking for df dx. Remember, that just means find the derivative in respect to x of f, right? So we're just taking f prime. That's just another way of saying it. Now, we can, probably the simplest way of doing this is rewriting this as a rational exponent. So we can rewrite f of x to equal x to the 4.5 if you want, or we could say x to the 9 halves, because this is x to the 1 half, and then we're going to get a common denominator and add those up. So as a result, we can see that f prime of x is just going to be 9 over 2 x to the, we have to subtract 1, so that's going to be 7 over 2. So that's probably the most efficient way of doing it. But let's go ahead and use the product rule here to see if we end up with the same thing. So I'm going to first rewrite this as x to the fourth times x to the 1 half, okay? Because we want to be able to use the power rule on this second piece as well. So here we get f prime of x equals 4x cubed, derivative of the first thing, times the second thing, plus the derivative of the second thing, so 1 half x to the negative 1 half, times the first thing. And then we can simplify that. This would be 4x to the 7 halves plus 1 half x to the, let's see, 7 halves again. Look at that. And then since they have the same exponent, we can add those. Those are like terms. So 4 plus 1 half is 9 halves, and then x to the 7 halves. So we can see that we get the same answer for the derivative either way. Again, if you have an efficient way of doing it like this, go for it. Don't necessarily have to use the product rule, but always keeping the product rule in the back of our minds. For whatever reason, products are hard for students to see. Quotients tend to be really easy. All right, the last one, there's actually, I probably didn't give enough information here to make this really clear, okay? Because the way I wrote it, students can be confused on what it's actually saying. I am not saying that u is a function. I'm saying that, how do I want to say this? The value of u at a certain point is 4. So for example, maybe, let's do this. U of a equals 4. U prime of a equals 2. V of a equals 1 half. And V prime of a equals negative 3. So these are the results at certain values, certain a values of these functions u, u prime, v, and v prime. And so u and v are functions, right? But we're not saying that the function u is 4. We're saying that the value of the function u at point A is 4. So we are looking for the derivative in respect to x of u times v, okay? And again, that's bad notation. I should say, what's the derivative of x of u times v when x equals a is really how I should be saying it here. But the bottom line is product rule here. So the derivative of this guy is going to be u prime times v plus v prime times u. And then from there, we're going to plug in what we know to evaluate at a. U prime of a is going to be 2 times v of a is going to be negative 1 half plus v prime of a, which is negative 3, times u of a, which is 4. So we end up with negative 1 minus 12, which is negative 13 for that first question on that problem. And then the next question, it says, what is d dx of negative 5 uv? Okay, negative 5 uv. Now we can apply a bunch of different rules to this. We can try and manipulate it however we want. But the one thing I want to know is this is a constant multiple. This is going to be the most efficient way to go about this. This is a constant multiple. So remember, when we have a constant multiple, we take it out, then we determine the derivative of the leftover, and then once we've determined that derivative, we multiply it by the negative 5. Well, if we're trying to evaluate when x equals a here, then we already figured out the derivative of uv right here. We did that work. So then this is just going to be negative 5 times negative 13, which is 65. Okay? So this is like function, this is an example of like function notation using the product rule. And my notation wasn't very detailed enough, but I think you can kind of get the idea. U and V are functions, so we took the derivative using the product rule, and then we plugged these values in at the point A. It could have been any point, any x value. Okay? So let's go ahead and double check that our answers are correct here. All right. And then, let's see, that one looks good. We have one more slide to go. Higher derivatives. So here, we've talked about the derivative, right? We've kind of got an idea of what the derivative is. Remember, the derivative is the slope of a curve at different points, okay? Or it's the slope of the tangent line, depending on what point along the x-axis we're talking about, okay? Higher derivatives, what's that mean? That means second derivatives and third derivatives, okay? We've also talked about how the derivative is the idea of a rate. It's the instantaneous rate. It's the steepness of a line. It's how fast a car is going, or the velocity of a car, you should say, particle motion kind of stuff. But higher derivatives, second derivatives, third derivatives, they have meanings as well. And we're going to get more into those meanings in the future. But it's a good idea to talk about taking these second and third derivatives just so we are familiar with the idea when we get to those applications, okay? So let x of t represent displacement in respect to time, okay? Let x of t represent displacement in respect to time. So in other words, if I'm looking at a graph, this is x of t, so this is time. So maybe I'm here to start with. Let's say that this is 5. What does that mean? That means at time t equals 0, I am 5 units away from what's considered home, or the origin, okay? And then as time goes on, maybe it does something like this, okay? What's happening? Well, as time goes on, my displacement, or my position away from a place, from the origin, is increasing. So that means I'm getting further away from the origin. And then up here, I turn around, and now I'm getting closer to the origin. And then I end up being on the origin, and then I go to the other side of the origin. So what's that look like here? What's that look like? If you were thinking of a number line and a person running back and forth on a number line, here's 0, and here's 5. So this person is starting at position 5, and they are moving that way. They're moving in the positive direction. They're walking this way, right? They get to this moment in time. So let's say that this point is time 3. At t equals 3, they stop and they turn around, and then they start walking back towards the origin. So we're getting closer and closer and closer to the origin. At this time, let's say that this time is 7, so maybe 7 seconds in, I'm at the origin. And now, as time keeps going on, I am now on the other side of the origin. So I walk that way, I turn around and I walk back, I pass the origin, and now I'm walking through onto the other side, okay? So that's kind of the context of x of t. Well, application-wise, if I take the derivative of that is the velocity. It's how fast I am moving away, or how fast I'm moving at a particular point in time. So you can see, derivative meaning the slope of the tangent line. You can see at this point, if I were to draw a tangent line, I would end up with a horizontal tangent. What's that mean? Well, the slope of that tangent line is 0. which means the velocity is 0. So I'm walking along here, and then I get to this point in time where I stop and I turn around. When I stop, my velocity is 0. Okay? So my velocity is 0 because I have a horizontal tangent. So that's the application there. Okay? The second derivative, we write it as x double prime, represents the acceleration. In other words, it's the rate of the rate. It's how fast my velocity is changing. Okay? And we'll get more in depth with that as time goes on. But the second derivative is the idea of acceleration. So if you're in your car and you're looking at your speedometer, that's giving speed, not necessarily velocity, but kind of the same idea, that is telling me how fast I am going. So that speedometer is actually telling me my derivative. Okay? Now my tachometer or my odometer is my position, if you would. It's telling me how far I have driven. Okay? The derivative of that is my speedometer. It's how fast I'm going. The acceleration is how quickly, well, let me rephrase that. The acceleration is watching the speedometer move. So if I am at, let's say I'm going 0 miles per hour. Well, as I speed up, you can see that my speed is increasing. That means I am accelerating. So whenever you see the needle move on the speedometer, that is acceleration. Okay? And then the third derivative is called the jerk. It's the jerk. It's the feeling in the car that throws you back, if you would. So if I am changing speeds from 10 miles an hour to 20 miles an hour, you're going to see the speedometer change, right? You're going to see that needle move. That needle moving is acceleration, okay? Now, as it moves up, my speed is increasing, so I have an acceleration. But let's say it's moving at a constant rate, right? It's moving at the same speed, okay? So the acceleration is constant. The jerk is if I'm going slow, and then all of a sudden that needle's moving up. So the needle is moving slow, but then it starts speeding up and speeding up and speeding up. If that's the case, if the needle is moving at a constant rate, you're not going to feel a force, you're not going to feel a jerk on you that throws you back. It's when that needle changes its rate is when you feel that jerk motion, okay? So the third derivative is the jerk. That one's a little hard to grasp or wrap our minds around, but these are the applications of higher level derivatives. Again, we're going to talk about particle motion a lot in the future. But with that said, let's go ahead and do a couple practice problems in just determining different derivatives. And I apologize, I have a typo here. I am giving you g of x, and I'm asking for f prime, f double prime, and f triple prime. That doesn't make sense. So I'm just going to change the name of that to f of x. Well, I'll keep it g of x, I guess, and then I'll just find g prime and all of those. So x cubed minus 5x squared plus 2. Okay. So if I want the derivative of this is just power rule and sum rule all put together. It's going to be 3x squared minus 10x. Derivative of 2 is 0, so I don't have to write it down. Then the second derivative, all the second derivative is, notice it's just got a double prime there. The second derivative just means the derivative of g prime. So the derivative of that is 6x and then minus 10. And then the third derivative is the derivative of the second derivative. So that would just be 6. And then we could even go further, even though I didn't ask for it, the fourth derivative, right? The fourth derivative would be 0. You might see it like this. You might see it like this. The fourth derivative, right? Roman numerals, fourth derivative. Okay? So with that said, that wraps up our lesson for the product rule. I hope you have a decent grasp of it. Remember to try and apply the product rule as often as possible. Anytime you see multiplication, you should be thinking product rule. Don't think derivative times derivative. No. Derivative of the first times the second plus derivative of the second times the first. With that said, if you have any comments or any questions, please comment below and I will get back to you. Otherwise, I will talk to you later.